Hey guys, welcome back to the last video on the final exam proofs. We're going to prove Rolle's theorem today, and the theorem says, let f be a function that satisfies the following three hypotheses. Number 1, f is continuous on the closed interval a to b. Number 2, f is differentiable on the open interval a to b. Number 3, the y values of the endpoints f of a and f of b must be equal to each other. Then we can say that there is a number c in between a to b such that f prime of c is equal to 0. So what's happening here is that, like we did in the lecture, we draw some graph right here. Say, let's call it a here, b here. And the graph is like a cap, like this. Then we can say the y value of f of b, y value of f of a must be equal to each other. So f of a equals f of b. In this case, what the theorem says is that there is a number c in between a and b right here, such that the slope of the tangent line at that point is equal to 0. This is what we want to prove. In order to prove this theorem, we need to understand the extreme value theorem and Fermat's theorem. If you haven't watched the video on Fermat's theorem, which states like so, if f has a local maximum or local minimum at c, and if f prime of c exists, then f prime of c is equal to 0. You can watch this previous video first and then come back to this one. Let's take a look at the extreme value theorem first. If f is continuous on a closed interval a to b, then f has an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in a to b. What this theorem says is that if I use this graph as an example, suppose f is continuous on a closed interval a to b, like this, then f has an absolute maximum, say f of c at x equals c, and an absolute minimum, say f of d, in this case is same as f of a and f of b, at some numbers c and d in closed interval a to b. Alright, we're getting ready to prove the actual theorem. One thing that we have to do before is to discuss the general outline of the proof. The outline for the proof is that we're going to consider three cases. Case 1 is when we're assuming f is a constant function. Then clearly, the derivative of constant number is 0. So f prime of c is 0 here, f prime of c is 0 here. So the first case of the proof is very easy. The second case of the proof is to assume that at some point x in between a and b, say right here, we are assuming that the y value of f of x is higher than the y value of f of a. For example, we are assuming f of x is greater than f of a for some x in between a and b. This is our second case. Did you notice that when we are assuming f of x is higher than f of a, clearly f of a cannot be a maximum because this guy is lower than this y value. The third case of the proof is almost the same as the second case proof, except that when we are assuming the x in between a and b, the y value is lower than the y value of f of a. So we are assuming f of x is less than f of a, in which case this f of a cannot be a local minimum or absolute minimum because this guy y value is higher than this y value. One thing I didn't mention in the second case is that f of b also cannot be a local max. F of b on the third case cannot be a local minimum too because we are assuming that f of a, f of b are equal to each other. Okay, let's jump right in. This is the statement of the actual theorem. we have to assume f is continuous on the closed interval a to b. You know what this means? It means we can use the extreme value theorem. So let's go back to our extreme value theorem. As long as f is continuous on this closed interval a to b, then f has maximum, then f has a minimum. So this is what the theorem says. Number 2, f is differentiable on the open interval a to b. This means we can use Fermat's theorem. The reason is, if you go back here, if f has a local max or local mean, and if this is differentiable at c, then we can use the Fermat's theorem. The third case assumption is f of a equals f of b. You know what this tells us? It tells us about the second case and third case. When we are assuming f of a equals f of b, then these points cannot be local max or local mean. Alright, let's start the proof. Case 1 is the simplest case, which is when we're assuming f is a constant function. F of x is equal to some number k for x in between a and b, which is the closed interval. Then derivative of any number is 0, right? So we can just say f prime of x is equal to 0 for any x in between a and b in the open interval. So you can choose, so we can choose any c in between a and b, which gives us a result, which is f prime of c is equal to 0. This is the end of case 1. Case 2. This is where we assume a y value f of x is greater than the y value f of a for some x in between a and b. You know what this means? It means if I go back to the picture, for some x in between a and b, the y value, this y value is higher than the f of a. In other words, f of a cannot be a maximum. So, extreme value theorem says that f has a maximum in between, like say, f of c at c in between closed interval a to b. Next, our assumption f of a equals f of b, and then assumption f of x greater than f of a tells us something about maximum and minimum. So we can say by the assumption, we can say f of a can't be a maximum. Similarly, f of b can't be a maximum. The reason is we are assuming some y value is higher than f of a. Some y value is higher than f of b, like this picture here. Y value f of a, f of b is lower than this y value. That's why these two values cannot be a maximum. So this maximum value f of c is located at c in between open interval a to b. For example, this maximum here happens at c in between open interval a and b. Did you notice that this maximum is now can be called with local maximum? Because see, left hand side, right hand side, all the neighborhood y values are lower than this y value. So we can now call it local maximum. This means f of c is a local maximum at C in between open interval A to B. This is a good news because let me put a box around this local maximum, and let me put a box around this second assumption, f is differentiable on the open interval A to B. Then what kind of theorem can we use? We can use the Fermat's theorem. If f has a local maximum at C, and if f prime of C exists, then what's the conclusion? The conclusion is f prime of C is equal to 0, and this is what we wanted to prove for the Rolle theorem. So here's the last sentence for this case too. Therefore, f prime of C is equal to 0 by the Fermat's theorem. And this is exactly what we wanted to prove, because then there is a number C in between A and B such that f prime of C is equal to 0. For the last case, the process of the proof is exactly the same as case 2, except this inequality is flipped. So what I'm going to do is I'm going to first copy this whole thing right here. And the next thing I'm gonna do is just change this to case 3 and assume f of x is less than f of a for some x in AB. Extreme value theorem says f has a, in this case, its minimum, say f of c at c in between closed interval A to B. By the assumption, f of a can't be a minimum, and f of b can't be a minimum as well. This means f of c is a local minimum at c in between A to B. Therefore, f prime of c is equal to 0 by the Fermat's theorem. Alright everyone, we have completed all the proofs for the final exam. Please study this carefully and get ready for your exam on December 4th. Dr. Hare and I have pre-exam and post-exam office hours posted on Canvas. Please check it out. It was my pleasure to work with you this semester, and I hope to see you next week.